So we'll just focus on three topics today. We're going to keep this very high level. You're not going to be experts at 1668 by any means. Some of you are well versed in the standard regardless. I just want to open up a few new perspectives for us to think about in this presentation. So I want to keep it fluid. I'm going to try to work through it in 45 minutes or so, and then allow for an opportunity for ideas and discussions at the end. So keep that in mind. So we want to focus on why do we have smoke control in buildings? That's the primary objective. How do we provide smoke control in buildings, and what are the expected results? Or what are the things that you need to be looking out for as surveyors? So we'll follow that line. Now, one thing that I'm very conscious of, a lot of projects, there's many people involved. There's mechanical engineers, electrical engineers, architects, surveyors. There's a number of disciplines involved. And when you have that, when you have too many people involved, it creates a greater circle of influence. So right here in the middle, we're trying to provide a great outcome for a project. As more people are involved, following through their own standards, everyone has their own role to play. It gets messy. And this is what typically happens at the construction site. Just keep that in mind as we work through it. There is a point to that. And one of the themes of this is that everyone needs to be aware of everyone else's discipline. You need to have some understanding of what smoke control is. I'm the mechanical engineer. It's my responsibility to design it and make sure it's compliant with 1668, but it's also everyone else's responsibility to understand it. All right, because it's not one individual making it happen. It has to be a team effort. Again, just highlighting what I just mentioned. There's a number of people involved. Everyone has a role to fill. Coordination is key in any project, right? And within your own discipline, it's my responsibility to provide smoke control for a building. The architect's forming up the building concept, energy consultants working. I guess the theme of this, and this is what I'm seeing in the industry, everyone's working in a silo effect. Everyone has their own role. And because the market's getting more competitive, everyone has less and less time to actually work together cross-discipline to see what everyone else is doing. Now that's a bit of a concern when you're dealing with a life safety system, right? That shouldn't be happening. All right, this photo is taken out of the UK, that Kishore mentioned to me here. Just kind of quickly defining the building surveyor's role, so we have some perspective as we work through this. You all know this, so I'll just highlight it. Your combination of experience, tertiary qualifications, and professional liability comparable to other building professionals such as the architect and engineer. So pretty much highlighting that we're all on an equal footing. We have an equal responsibility. Conduct critical stage inspections of building work as it progresses, so that's obviously a key role we're going to come back to. This one here, obviously since 2010 when private certification came in, the role of the surveyor has evolved. It continues to evolve. It continues to evolve in my discipline, where we're actually held more responsible than ever. We're given less time to document. Fees are lower, but ironically, we're given more responsibility at the same time. Okay, get the design right from the beginning. This is a key one. So obviously, surveyors, engineers, we're typically not involved in a project until the project planning has already been established by the architect, working through council requirements and trying to get planning approval for the developer. So the level of involvement in the team is actually quite small for the largest portion of a project. But ironically, and I think I've talked to a few of you guys, I know that we're all in a similar boat. You might be engaged after a project's been developed over a period of time, and then you have to go in and advise recommendations and changes to that architectural planning. So it forces the architect to redraw, as opposed to getting all of us involved at an earlier stage so we can have a better plan of attack when it comes to setting up the building. I'll show you a couple examples of that later so you can see. But if you have an idea, a mindset of life safety going in, if the architect's familiar with the strategy, specifically the smoke control, then they'll have a better idea of how they want to lay out the building. Where do they locate the toilets? Where do they locate stairs? It doesn't have to be a redesign exercise after the surveyors are engaged. It's done once, it's done properly, and then obviously that saves a lot of time and hassle. Yeah, they use with fire engineer architects to ensure a strategy, so I'm going to talk about that a few times. So again, it's a team effort. If mechanical engineer, I'm responsible to highlight which options are available for smoke control for a building. But it doesn't mean I'm telling everyone what to do. I think it needs to be a team effort. The fire engineer, the architect, the surveyor, and the mechanical engineer should be planning the strategy from an early stage. And by doing that, if everyone's planning the strategy together, you have some ownership to it. You have some understanding of what the concept is and actually how it works. All right, so why smoke control? Starting with our chart there, obviously the whys are quite simple. We want to protect occupants in the building. We want safe access out of the building if there is an event. We want to give the fire brigade an opportunity to fight it. The developer would be looking at saving any property loss in the building. If the fire event's small, we just want to clear the space. Friends, family, and colleagues, we have to look out for the future of the building. Anyone occupying a building could be our own family and friends. We just have to keep that in perspective. I think too often we get caught up in the regulations and standards and design elements and coordinating in a tight time frame. We kind of forget why we're doing it in the first place. We're doing it for us, for the public. And that's my mandate as a chartered engineer. It has nothing to do with making the client happy or the developer happy. I have to protect the public. That's my duty of care. All right, so perspective, we just want to obviously look at the reality of what can happen. Everyone's familiar with what happened in Grenfell. It was a disastrous event a few months ago. Now, I saw this, it was a bit interesting. When I saw it in the news, there were a few comments on LinkedIn, there's some back and forth on this. Well, how did this happen in the first place? We need to work out why. Obviously, we know there was an aesthetic upgrade to the facade. There was some building material that's highly flammable that wasn't actually certified to be used properly. I think there was a fridge down in the basement that exploded. It was a spark. And I don't know how it traveled up, but that led to a domino effect on the building. And obviously, as soon as that panel lit up, there was a coanda effect, so all that hot gas started kind of blanketing itself on the surface and then spreading very quickly. Now, there's only one, my insurance broker actually, he used to live in a building like this in the UK, so he's familiar with it. We had a chat about what it was like. There is one single staircase, it's very narrow. I don't know when it was built. Was this in the 70s or 60s? So obviously standards and regulations back then would have evolved since then. And this right here, I don't necessarily think this could be fake news, but I did read an article that said either the ownership body or the residents decided they didn't want the disruption to their own building with retrofitting sprinklers in the building. Again, I don't know if that's true, but in this just keep this one in mind. We have a lot of buildings in Perth that are out of date, that are outside of the current regulations and standards. You're going to be approached by clients to bring them up to standard. They might change classification from 5 to 6. When you change your classification, it triggers it to have to bring it up to the current regulations, doesn't it? Obviously, the client's not wanting to spend a lot of money. In this case, I don't know what the motivations were. I'm only going to speculate. They're looking at a visual upgrade. They're looking at improving property value. I think they did try implementing fire doors internally, but was their money best spent this way? Whose responsibility was it to tell the developer at the time that maybe they should have looked at other investments within the building? It's all hindsight. Just keep that in mind. We have an ability to influence the developer to spend his money wisely. So obviously, we'll talk about air pressurization, and smoke control. If it was implemented in this building, I'm not saying it could have been, it would have just bought more time. It would have saved a few more lives had they spent the money there in the first place. I just read a few articles on that. I found it interesting. Everything that you read about the event had nothing to do with fire doors, access and egress, looking at the cladding. That was a big trigger. This is what triggered the fire. But obviously, as a mechanical engineer, this is what I do. That was the first thing I'm thinking, is how they didn't allow them enough time to get out. Fire control strategy was to stay in your room and wait for the fire brigade, which would have been a solution that council would have accepted. But then you also have to think, if that's you in that building, is that common sense? Are you going to feel willing just to stay in your room? Probably not. So think about yourself. Think about the end user. What would they actually want to do? They want to get the heck out of there. So buy them time. All right, so we're talking about smoke control today. Let's get some perspective on it. Again, let's have a look at what are we dealing with. I grew up in California as a kid. I do remember a few bushfires in the area, but I've never personally experienced an event myself, so I don't have much perspective on it, really. I've never been in a building that's gone off. Let's have a look at this quickly. This is just there's no audio to it. Just showing how quickly a fire spreads. The Christmas tree. Don't focus on the fire, focus on how quickly the smoke billows up. And how quickly your visibility is gone. 28 seconds. Less than a minute, you can't see. So this is what they would have been experiencing when they had to run down the stairs. Obviously, those events were a bit there. That's what can go wrong. We'll just show you what I'm not going to show this entire video. I'm going to send links to these so you can check it out on your own time. So in the atrium, they're setting up a smoke test. So this is commissioning for the building. They're just ensuring that the fire control systems work. The FIP is showing them the zones which need to extract, ensuring the fans are doing their job, and confirming how quickly they can evacuate the zone. You can see from a few of the slides here, that's just showing actuated dampers opening and closing, fire curtains closing, fans operating. This cleared out, and there's the print screen of the FIP, the building control system. It cleared in about 10 minutes. The smoke curtains on the lifts shut. It's a makeup air path. Showing fire stopping. We'll show you examples of how that's done incorrectly. Exhaust damper opening to extract. Alright, so that was a successful smoke test. It's important to visualize how the systems are going to be tested, just like you saw when you're designing, and when you're working with the mechanical engineer and the architect, so that you're sure that you covered all bases. Alright, so we kind of highlight why do we have smoke control. We've shown a few examples. Now we have to look at how. So our standards and regulations derived from NCC in 1668. That's what those are they're telling us how to design. We want to look at working together as a team. We've talked about it a few times already. Compile design certifications from the relevant consultants, from the fire engineer and the mechanical consultant. Confirm commissioning and testing has been provided in the end of the construction. Ensure accountability is shared, and for the surveyor, you want to make sure you have an understanding. And you ask questions of everyone on the project, especially me. Make sure I know what I'm talking about. Make sure I have the design correct, and make sure that you're familiar with it. So when you're on site, witnessing a test or doing an inspection, you have perspective. Again, this is just showing you what's telling us. This is our mandate, 1668 NCC Part E2. Again, looking at responsibilities, if this is a team effort, obviously they're looking back on that Christmas tree that lit up. You're working with an architect and a fire engineer. Where are smoke paths within a building? Air and service ducts. Again, that's our responsibility. If we're running air through a building, we have to ensure we know where the fire compartments are and how do we protect one zone from another using fire dampers, smoke dampers, and smoke control. Obviously, HVAC systems themselves, either exhaust or air conditioning systems, are going to contribute to transferring smoke around the building. Exhaust systems, same thing. Also have to be mindful of gaps between walls and floors of construction will transfer smoke. So we can do our job. The contractor can make sure everything's airtight, dampers are installed correctly, but if the builder hasn't done his job, then that's going to compromise the entire system, isn't it? To some level. So just showing where all the risks are. They're everywhere. So everyone's needing to be aware of it. These next few slides are just kind of highlighting the key sections of 1668. Again, you won't be experts. We're just going to touch base on it to give you perspective. A lot of you are already familiar with this, so we're not going to waste too much time on it. Ductwork. So obviously we run ductwork around a building to provide air conditioning, smoke exhaust, zone control, toilet extraction, kitchen exhaust. So it's our job to ensure that we size the ducts correctly in the first place to cater to the air quantity or the air volume. But also when we're on site inspecting, we want to make sure the integrity of that ductwork is proper. One key problem that we've seen a lot in the industry there, if you have a duct, see these supports here? Say that's just a sheet metal duct right here. A few more slides will have a fire damper. If there's a fire damper fixed directly to that with a hard connection to a flange, that's technically non-compliant. Because if there's a breakout in fire in that ceiling and these supports go, say that's a 5 or 10 meter run, then that duct is going to collapse. The weight of that duct is going to pull that damper off the wall. So you're meant to have a break on the damper connection with ductwork. So that's something that I would have to inspect, something that you'd also should be aware of when you're walking around site. It should have a slip joint connection. Because again, you don't want to lose the integrity of your smoke control. Putting all the effort into the design and construction of it, that one little item could compromise it. Be familiar with the different types of dampers. You can have motorized control dampers, which form a smoke control strategy. Intumescent, we know once they close up from high temperature, that's it. They're isolated and they have to be removed and replaced. All right, the next section, fire protection of openings. to maintain integrity between fire zones. That's right. We talked about the breakaway joint here, which is critical. That's another one. So we might have a fire-rated riser we're coming out of with exhaust ductwork. Could have 2 or 3 ducts coming out of a riser, picking up, say, 3 toilet compartments on a floor or between floors. But our air quantity is extremely low. It could be 200, 300 liters a second. So the size of that duct could be 200, 250. Now, and I decide, okay, I'll put the duct here. I've got a fire damper in that duct. The duct is 200 wide. I need access to get to that damper. That duct is already small as it is. It's physically impossible to provide a proper fire damper that has access. So to do it properly, I have to open up. I've got to open up my ductwork to get into that riser, so I can fit an access panel in the duct, so that I can actually get to it, and I can maintain it. But that doesn't really happen. I've seen so many examples where that's simply not done. And I'll show you photos of where that's not done. Now, separation of dampers. If you have 2 small ducts running side by side in a brick wall, which is intended to be fire rated, it's 60, 60, 60, 60, so you have a 100 mil gap between the ducts and the dampers, the integrity of those penetrations is gone. How's the builder going to give you a clean cut with a 100 mil gap in brick? So that right there, if you see it on a design drawing, say it's on one of my drawings or another mechanical consultant, you might want to voice it up and say that doesn't look right. You're squeezing it in a bit tight. So it's just taking a step back and looking at how do I maintain it, and how do we don't want to compromise the integrity of the installation. You minimize those risks at the design table. General requirements. So location of openings, direction of smoke spill. Obviously, we have to provide separation between any smoke exhaust path and an intake path. We're not short-circuiting. So again, that's a planning issue. That's a planning issue with the architect, with surveying. We might have a good strategy early on that allows us to set it up very easily from the beginning. I've been in situations where we're trying to find a makeup air path, but we don't have many options. We need to keep, if it's greater than 2,000 liters a second on a smoke exhaust, you need 6 meter separation. And if I'm given a plan and I don't have that many options, then what it typically does is it forces a higher cost. I have to run the ductwork a longer length, which is adding unnecessary cost to the project. But if we had a strategy from early on, then we could actually plan it from the beginning before the architect starts forming the building, which will save cost. And also, at that time, when you're explaining it, you're all learning the process. You're understanding why you made that decision. Noise control, that's critical. The standard says in an escape path in a stair, you can't exceed 80 dB. I think it's 80 plus. So again, protecting the occupant and getting out so they can at least hear an alarm or hear instructions. Fire door pressure differential, we'll look at that in a bit. Control indications. Baseline data. The consultant's documented, he's worked out you need 10,000 liters a second. That's your baseline design data that's been provided by the fire engineer. We want to see that at the commissioning test phase. So this is something that needs to be recorded and witnessed by both of us. Kitchen exhaust. That's another means of smoke management. The new standard 1668 2015 was adopted recently. It took over from 1998. There was a few minor changes to it. Obviously, kitchen exhaust fan, you keep it running on a fire signal as opposed to a shutdown. This has been made clearer as well. So the hood supplier needs to provide a spark arrestance system within the filter in the hood so that there's no risk of an explosive event within your exhaust path. Suitable access every 3 meters. This comes up a lot. On that job, we have old hoods. They're taking it all out, they're demolishing it. The kitchen exhaust system's perspective-wise well over here, crossing over other tenancies down on ground. The developer wants to master plan it and just kind of deal with this separately. So what we're doing there is we're actually removing all this kitchen exhaust ductwork, relocating that fan deck over here, and creating a new common riser. So that riser, it is in a masonry shaft. We need to fire wrap that ductwork going up, but also we need to provide access every 3 meters. And I've made that very clear. When I brought it up to him, he was like, oh, okay. Almost like he wasn't going to do it, or he didn't really think it was necessary, but I said, no, you have to. So a lot of times when you have a D&C where a consultant's not involved that doesn't know that rule, they will do it without providing access to clean it. So the duct builds up with grease over 10 or 15 years, and that becomes a risk. It's a fire risk. It starts growing. So maintenance is another one. If you can make it easily maintainable, it's more likely to be maintained. If you make it difficult to maintain, it's not going to be maintained. And that right there is a risk to the design and life safety. I talked about ducts going into a wall, making sure you can actually get to them to test them. Make it easy from now. If you make it hard, it won't be. They'll never look at it. System shutdown. So in one compartment, the strategy might just be to isolate the fan. so you're not spreading the fire typically in a smaller compartment. The rule used to be a rule: anything over 1,000 liters a second, you're mandated to shut down. They've since changed that rule, so it's actually it's up to the design team. I don't really understand the logic behind that. 1,000 liters a second in the first place. I mean, I think a lot of times standards are written by others that come before us. It doesn't always mean they're right. We need to have question the standards at the same time as we're designing to find a practical solution. Simple is better. If it's a simple design, simple concept, it's more likely to work than not. So I always try to take the path of least resistance and not get bogged down too much in the details. This is an interesting one. So 1668 and 1998 gave you a number of options based on classification of building, how many floors. This new standard really simplified it. It's allocated all of those options into zone pressurization. So it's putting more responsibility on the fire engineer and the mechanical consultant to work out the strategy. But this typically is the preferred strategy in a building over 25 meters. Is to, if you have a fire-affected floor, you want to extract it. You have dampers set up so that you close off your air handling system is feeding that floor, shut down. You extract it out completely, and then you maintain pressurization on the non-affected floors. You refer to it as sandwich pressurization, which is what Stephen and I have done on 8 Davidson Terrace. Kind of why I asked the question, how many of you are involved in projects greater than 25 meters? How many of you had experience with zone pressurization? About half, maybe? Yeah. So again, if a job like this comes up, it comes across your table, and you've never done it before, you want to get some understanding from now, so that you have the ability to converse with the mechanical consultant and the fire engineer. There's nothing stopping you from getting a job of this nature, any time. So study from now, especially when the market's quiet. We want to just brush up on it. It's not difficult. Pressurized floors that are non-affected, exhaust floors that are. This is the key element. So if you're trying to get out of the floor, you want to make sure that the pressure behind the door, the escape door, is no greater than 100 newtons. You don't want to make it difficult to get out of the building. So that force is translated based on the pressure differential. So again, you can allow a 20 to 80 Pascal difference between affected and non-affected zones. Confirm suitable airflow across the door. I'll show you an image of that. So this is something you need to witness, and something I'll have to witness as well. When the commissioning agent's doing a smoke test, we want to make sure there's an average 1 meter a second across the escape path doors and the fire-affected floors when you're leaving that floor, to prove that you're getting a pressure differential, and also to make sure that there's no risk of smoke ingress into the other floors, into the escape stair. This was recently introduced into 2015. Exhaust smoke from the hot smoke layer to maintain smoke above the egress paths. Now, honestly, I don't have any experience with this at this point. So again, the fire engineer would have to drive this solution. They pretty much tell us the exhaust quantity. We provide the fans to suit. Single fan permitted. Protection of exit, so a stair, escape stair, either vertical or horizontal. Again, know the building well. You're working with the architect. You have to identify. This actually comes from you. If you have an escape path, like I think the rule 60 meters, greater than 60 meters, then we have to pressurize that escape path. So again, we're working together on that solution. If you're planning it from the beginning with the architect, you might be able to get rid of that option. Again, smoke control is fine. Having a 80 to 60 meter run to provide smoke control, that's great. But wouldn't we rather not have that system and have a safer escape path? A lot of projects look at this 25 meter rule. You'll see many jobs that kind of just come right underneath the 25 meter rule, so they save extra cost of sprinkler requirements in the zone smoke control systems. Now, that's an interesting one, because we obviously that's an added cost to the developer. Say you're at 24 meters right at the top level. The standards say we don't need to provide smoke control on that escape path. But does that mean the developer doesn't have to do it? No, it doesn't. It doesn't at all. He's going to save the money, though he doesn't want to do it. If we come from a point of thinking life safety and say that's the key motivator on a project, depending on the application, then maybe it will be thought of. So again, the standards tell you to do something, it doesn't mean you just have to do the bare minimum. Maybe it's still something to consider at a briefing stage. Weigh up the risks and opportunities. Air purge, that's pretty basic. get a zone extracted, purge there. Lift shaft pressurization, very similar to stair pressurization. To be sure, mindful that we provide relief at high level, architectural relief louvers. Given the piston effect of the lift, we want to make sure that smoke can get out at high level. Car park systems. It's an interesting one. So for car parks, we need to have, on a signal, fan drives to 100%. Again, you have to give the fire brigade the option of isolating it, shutting it off. All the ductwork systems, everything has to be rated to this condition here, so there's no failure of that extraction path. And same as kitchen, you can't have any fire dampers in the escape path or the exhaust path. This is going to be an interesting one in 5, 10, 15 years when electric cars are common. It's probably still a bit working off this old standard. That's an interesting point. What are your thoughts on that? So say 20 years from now, every car is electric. The entire driver with the standard for us is to get rid of carbon monoxide and emissions in NOx in a car park, based on size, number of bays. 20 years from now, when they're all electric, we don't have any emissions to deal with. But as a surveyor, fire engineer, would you actually still look at it depending on the design to provide extraction?